Good morning again. We are ready for our third session, computational math at a planetary scale. We are interested in this session to discuss problems and topics and areas that affect our planet as a whole. Obviously, the bird's eye view to problems that are large-scale problems for us. We have seen at the beginning a session on sort of human-centered issues, healthcare, medicine. We talked about societal issues in the second. What we'll be focusing on is how computational math is used to address problems that have to do with technology in general, transportation, energy, but also the planet as a physical system. So problems that have to do with geophysics and our prospect to understand and be prepared perhaps to respond to emergency that have to do with perhaps climate or earthquakes and so on. Again, this is a very limited preview of all the activities that are present within ICME and at Stanford. But the three speakers that we're going to see in a minute actually are representative of three of the schools on campus. So we have obviously ICME participation in all of them, but the School of Engineering is represented, the School of Earth Sciences, and the School of Humanities and Sciences. So the broad topic is difficult to sort of summarize in few words, but it's very clear that all these problems are problems that affect our planet, can be tackled with advances in computational mathematics, algorithm computing, but also more and more by combining our ability in acquiring and using data that comes from the physical world into our algorithms and sort of fusing the information from classical physical sciences and more modern data science and analytics. So without further ado, it's a pleasure to introduce the speakers in this session. We have two faculty at Stanford and a student providing short, brief summaries of their research work. I want to start immediately by introducing our first speaker, Professor Catherine Gourlet. She's an assistant professor in the Department of Civil and Environmental Engineering here in the School of Engineering. Catherine received her bachelor and master from the University of Delft in the Netherlands, and then her PhD at the Von Karman Institute for Fluid Mechanics in Belgium. She has been active in simulation of fluid mechanics problem in a variety of disciplines, variety of areas. And she has been at Stanford as a postdoc first, then she took a short period where she was on the East Coast, and then she came back as an assistant professor here at Stanford. She received the NSF career recently. She has been a Marie Curie fellow, and she's recognized for using both simulations and data to actually approach problems that have to do with sustainability, both in cities and in sort of built environment. So without further ado, Catherine, thank you for being here. I'll pass it over to you.
Thanks, Gianluca. Okay. Good, so I'm going to give a very quick introduction to computational wind engineering for sustainable buildings and cities. So 60% of the world's population will live in urban areas by 2030, and cities account for 60 to 80% of the energy consumption and 75% of the carbon emissions. And these are just a few of the facts that indicate that there's really an urgent need to design safer, more resilient, and more sustainable buildings in urban areas. There are actually several ways in which wind flow in a city or a building affects safety, resiliency, and sustainability. One of the first ones is that when you design new high-rise buildings, it's imperative to ensure that public spaces will still be safe and comfortable to use for pedestrians, because you could get locally very high wind speeds. You could also think about harvesting urban wind energy, or about incorporating water features or green areas or green roofs to mitigate urban heat island effect. Pollutant dispersion is important because it determines air quality. Natural ventilation could save energy and provide better indoor environments. And then wind loading is important from a resiliency point of view. And the last three are the ones that we have focused our research on mainly in the last couple of years. So I'll give you a little more background on this. So pollutant dispersion is important from an emergency response planning point of view when there are accidental releases. But we're also very interested in it from an urban planning point of view, because there is a well-known connection between air pollution and respiratory and cardiovascular illnesses. The plot on the left, for example, shows the occurrence of COPD as a function of long-term exposure to particulate matter. Air quality is also, outdoor air quality is important when you start thinking about ventilation strategies and the relation between outdoor and indoor air quality. So that brings me to natural ventilation. And with natural ventilation, what you try to do is you try to use the natural forces of wind and buoyancy to bring fresh outdoor air into a building and to also cool a building. It's very interesting from an energy point of view because 41% of the total US energy consumption is in buildings. And heating and ventilation and air conditioning accounts for 40 to 50% of that energy consumption. So if we could have a more widespread use of natural ventilation, we could save a lot of energy, 10 to 30% of the total building energy consumption. In addition, we know that bringing in fresh outdoor air is actually good for health. It increases well-being, and it also increases productivity of building occupants. And then the last application that we are focusing a lot on is wind loading. So in the plots on the right here, you see the damage path from a tornado on top, and then you see damage due to a hurricane on a high-rise building. And if we could make buildings more resilient to these extreme wind events, that would actually be a very big advantage from an economic point of view. The average insured loss per year for extreme wind events is 7.78 billion. And in the cost this year, there was 27 billion in insurance claims. So our goal here is to better try and predict what kind of loads buildings would experience under extreme wind. So when you think about all of these different applications, there are two big challenges that always come back. The first one is that these flow problems are governed by a lot of natural variability. They are determined by the larger scale weather phenomena, which will determine the flow that actually happens in the city or in the building. And they're also governed by how the city or the building is being used, how much traffic is there, how many people are there in the building. The second challenge is that these are very complex flow problems. So it's a highly turbulent flow, you have a large range of scale, and you need some sort of reduced order model to represent these complex physics. So when we try to predict these problems, we need to take into account these challenges. So what we do first is that we think about what are the uncertainties due to variability in these operating conditions. And then second, what are uncertainties because we have to use these reduced order models. Then we run a large number of simulations to propagate these uncertainties. So we consider all of these possible conditions such that we get predictions for probability distributions for a quantity of interest. And then the thing that we focus on a lot is to compare our predictions to actual field measurements. Once you have this type of comparison, you can also do data assimilation, right? You can compare your prediction, your probability distribution for your prediction with your measurement, and then do data assimilation to get a better characterization of your uncertainties, and then to also get a better prediction in the end. And this is especially interesting because we see a very quick increase in the number of urban sensors or building sensors that is being available and the amount of data that we have to improve these predictions. So to wrap up, I want to show you results from one case study where we try to predict the wind field on campus. And predicting the wind field is really the first step in addressing any of these applications that I showed you at the beginning. So here we focused on characterizing variability in the incoming flow conditions and then using data assimilation. So what we did is we set up an experiment on campus where we have 6 wind sensors that continuously measure the wind speed and the wind direction. And we used 2 of the sensors to do the assimilation and then 4 of the sensors for validation. The experiment was run for 3 days in total. And then to see if using data simulation, we can actually get better predictions, we also compared this to the more traditional method. And in the traditional method, you would look at the nearest weather station and just look at hourly average data over these 3 days and run a deterministic simulation for each hour. When you look at the results, what you see is, first, I'm focusing here on the assimilated sensors. And of course, there you see what you would expect, right? When we do the assimilation, you get the blue probability distribution, which compares very well to the experimental data, which is the red distribution. If you use the boundary conditions from the weather station, that comparison is less good. We expected this because we were actually trying to match this data, right? We use this data as input. However, when we look at the validation sensors, we see that that improvement does really carry over to give us better predictions. So in summary, what we're trying to do is we want to advance the state of the art in predictive wind engineering to quantitatively support sustainable building design and urban planning. And in order to achieve that, we really look at combining field measurements, wind tunnel measurements, and models with different levels of fidelity using techniques from uncertainty quantification and data assimilation, and then doing a lot of validation with field experiments. So that was all that I had, and I look forward to your questions later. Thank you.
Thank you very much, Catherine, for that summary. Very exciting indeed. Let me introduce the second speaker. We will have a chance to perhaps discuss a little more with Catherine afterwards in the Q&A session. But let me, as I said, introduce the second speaker, who is an ICME student, an ICME PhD student, Rahul Sarkar. Rahul is working with two advisors. One is Professor Biondo Biondi, who will be the next speaker, and the other is Professor Andras Vasi in mathematics in the mathematics department here at Stanford. And Rahul is interested in a number of research topics. His research is mostly centered around seismology and developing of tools for that. But in this talk, he's actually exploring a different side, which is the use of quantum computers, specifically for large-scale problems related to sustainability. And I want to mention that Rahul has been also involved in teaching over the last academic year, has been teaching our first ICME short course on quantum computing. So without further ado, Rahul, take it away.
Thanks, Gianluca, for the kind introduction. In this talk, I'm going to not deal with the question of whether a quantum computer will ever be built. So some of you must have already heard that there are some small-scale quantum computers and some interesting things have been done with it. The focus of this talk is going to be assuming that there exists a quantum computer that is capable of solving some realistic problems that we expect quantum computers to be able to solve eventually. What can we do with it? Are there any computational problems that exist in the sustainability domain that could be? So, what are some of the computational problems in this space that would be the best candidates to solve using quantum computers? Okay, so in 2015, the United Nations met in the General Assembly, and then they basically laid down 17 sustainable development goals that they plan to achieve by 2030. And so I'm going to speak mainly about 4 of them, which are particularly good candidates for application. So the first one is to reduce the hunger to absolute zero. So as you can see on this slide, so out of about 700 million people who are affected by this issue, in Africa and Asia, the number is around over 600. So by far, the issue that of hunger, people dying from food shortage essentially affects Asia and Africa. And this, for example, is particularly problematic when children don't get nutrition in their early developing years, because that actually reduces their brain development. So the second one is good health and well-being. So this snapshot on the left is a virus model of coronavirus. I don't need to mention exactly what's going on, but we are living in a situation where any kind of progress in being able to test out drugs would be especially welcome. And so currently, right now, we just don't have the capability to simulate complex molecules, which are needed to, speed up the process of drug discovery. Okay, so the third one that I have chosen from the list of 17 is affordable and clean energy. And this is the graph on the left is basically the over the last 7 years roughly. So what is the forecast of energy production in terms of various sectors? And as you can see that the renewables are still quite low in this list. And we want them to eventually get higher. So we want to transition from this polluting sources of energy to something cleaner. But there are some technical challenges involved in all of this. Okay, and the fourth one is climate action. So in the town I'm from, Calcutta in India, so there was a cyclone last week, and well, so the number of people who died were around 100. It cost around $13 billion in US dollars in damages. Compare it to Hurricane Harvey from 2017, that was around 125 billion. So the main thing that I want to stress here is that the amount of other than lives lost just on the economic scale. So if like just think about the scale of these damages that the hurricanes have been causing in recent times. It's really like each one is about a few $1 billion. And if you could do something to prevent them or reduce their magnitude in some sense, that would be quite welcome. So the point is that in each of these areas, there are some computational problems that a quantum computer can help us to solve. So let's actually go through them. So I'll just briefly start by mentioning what a quantum computer can and cannot do. So a quantum computer is quite different from how a classical computer works. So classical computers manipulate bits of zeros and ones, while a quantum computer manipulates quantum states. And so a quantum state could be in a superposition of something which is called the zero state and the one state. But so now people do think that quantum computation, the power of quantum computers is strictly more than classical computers. So it is known that like perfect quantum computers can do exactly what classical computers can do, but it is not known if this is strict. So quantum computation is definitely as powerful as classical computation, but it is not known if it is strictly more powerful. So it may turn out eventually that and the situation is really like P versus NP. So people believe that the problem class of NP is strictly bigger than P. But it's an open question if it's P is equal to N. And similarly, it's an open question whether quantum computation, the power is equal to that of classical computation power. But probably we may or may not live to see these questions resolved in our lifetimes. One quote that I really like to say, so given the caveat about quantum computation, what do the experts believe? So I put out a quote from one person who is working in this field, Michael Friedman, also happens to be a Fields medalist for work in some completely unrelated field in geometry. So the part of the quote that I really like is that what it says, so what we don't know is that quantum computation is the uncorrupted, lossless, frictionless way for a machine to think. And once you have that idea in your head, it is very hard to go back to classical computation. So that's what Michael Friedman says. And Scott Aronson, who is another really well-known personality in the field, says that the killer app for quantum computers will most likely be simulating quantum physics. And this really is the application area that I'll target because this is most likely what is going to happen in the near term. So the first application is based on hunger mitigation and in agriculture. For example, producing nitrogen-fixing fertilizers is quite energy intensive. And you can speed it up if you could test out fertilizers a bit faster. Similar problems exist in drug discovery, CO2 capture and catalyst design. So if you could take out the carbon dioxide from the atmosphere, that would be really helpful. And again, you have to simulate chemical reactions in any of this. And there are some other applications in high temperature superconductivity. So if you could develop these materials, then you could transmit energy without much losses. And similar chemical simulation of chemical molecules generally also exists in the domain of better battery design. So all these applications that I list here are going to require eventually large-scale quantum computation capabilities with error correction, so probably hundreds of thousands to millions of qubits. And the only way to do this is to fund the research right now. So take some billions of dollars that are lost every year and do it now. So towards that goal, I have worked on a few things in my own research. And so this is going to be the last slide. So we have been working on a class of quantum codes, surface codes, which use these things. So these are surface codes which are generalized some existing quantum codes. If you want more information on this, you can write to me later on. But they come in two distinct families, the checkerboardable ones and the non-checkerboardable ones. Checkerboardable codes, it turns out, have already been discovered. These are the Kita historic codes. Again, so I'm not going to spend any time on this. You can write to me about if you want to know more about this work. And with that, I will thank everyone for listening, and please contact me at this email for further questions. Thank you.
Thank you, Rahul, for the presentation and for the discussion about opportunities for quantum computing. I'm sure this is on many people's mind, what this could actually be. Certainly, the next speaker is being pushing the envelope of computing for actually quite his entire career, and I'm excited to see actually how more sort of current computers are actually used to push the boundaries of research. So let me introduce Professor Biondo Biondi. He is the Barney and Estelle Morris Professor of Geophysics in the School of Earth Sciences here at Stanford. He's also the chair of the department. And Biondo has a esteemed career in geophysics, especially in the analysis of prediction of earthquakes and seismology events and all the mathematics that go with it and all the modeling that goes with it. But as I mentioned before, specifically what is exciting about Biondo's research, and also the connection that he has, the strong connection that he has to ICME, is the idea or the effort in pushing the envelope of doing simulations at larger and larger scales or newer and newer platforms, and also how to incorporate data into the physics simulation that he does. So without further ado, I'll let Biondo start. Out to you, Biondo.
Good morning, everybody. I'm happy to see you here online. And I'm coming back to the present from the future. I'm going to talk about very much along what Catherine presented a few minutes ago about resilient and sustainable cities and how we can collect geophysical data and apply sophisticated both physics-based analysis as well data science-based analysis. So now I will start sharing my screen and my slides. And here it is. So this is a nice graphics representing the experiment that we had going on almost for 4 years of fiber optic seismology at Stanford. You may recognize the map that is the engineering quad, and there is the ICME building as well. And we basically put together the technology of turning fiber optic cables into seismic sensors, together with the idea of leveraging existing telecommunication infrastructure, like in this case, current cables on the Stanford campus, to record seismic data. And we have been doing that for almost 4 years, and we've been pioneers on that, and now about 10 campuses around the world are doing something similar. Just a well-deserved credit to all the young and at least younger people involved, from a senior research engineer to a PhD student. And I'm going to show you 3 vignettes, 3 examples of the application of this data. And on the top of the slide is the correct attribution, which person was involved in each of the examples. Let's start with one that unfortunately is very timely, have to do with COVID and the COVID lockdown. Obviously, for authorities, it's very useful to monitor the traffic in this situation to understand what is the correlation between infection and mobility. And we actually could do that. We do have a fiber under sand hill. Don't know if you know Stanford campus is basically on the northwest side of campus as indicated on the map. On the left, the fiber goes from basically down on the flats at the Stanford Hospital all the way almost up to 80 to Slack to be more precise. And what is exciting that on the right, we have basically a vehicle counts over the time of the lockdown. And the other lines, the dashed and the solid black line, corresponds to mobility information made available by Apple and Google. And you see we have quite a bit of correspondence, but we have infinitely higher spatial resolution, with the important point that we have no problems with privacy, because we just fill the cars. We don't know whose car, which car it is. And also there is no sample bias. The phone mobility information is biased by ownership of the phone and by the fact the owner allowed to look at their spatial information. I should say that this work is been submitted to Science Advances and has also excited the city of San Francisco. So the next step here that we have been talking with the city of San Francisco is to collect data this summer to have a real-time effect on traffic in different parts of the cities of the lockdown, or thankfully now we are freeing up. Another one is much more typical geophysics, but again, using the fiber along Sand Hill. On the left, we see two kind of snapshots of data. On the top is an earthquakes in the hills behind Stanford, and on the bottom, on the left, are the surface waves generated by cars. And these surface waves generated by cars by the earthquakes basically allow to invert or to estimate the soil properties from 0 to 120 meters under the surface. That has very much use for both civil engineering, for earthquake hazard predictions, as well can be done in real time, basically by the hour. And so you can see developing problems in real time, let's say sinkhole under a road. The last example that I'm going to discuss is more resilience of cities to seismic and to earthquakes. Unfortunately, in the Bay Area, we have a lot of them. The map on the left shows the database that are of earthquake that have been recorded by our array in the past 3.5 years, according to the US SDGs catalog. So now we have thousands of events. We trained a convolutional network, and that is the graphics from the middle that want to basically say we have now a lot of good labeled data. We train a convolutional network, and we could find automatically the known earthquakes in the catalog. But for the local ones, we can actually find one that is not in the catalog. This is actually on Stanford campus. And the idea here that using very dense arrays of fiber optic, we can have an order of magnitude better understanding of local seismicity and have a better handle of the seismic hazard to society. These are the three examples. Now, just looking at the future, this is a graph that represents the number of potential seismic sensors using installed fiber optics. And when I started the project, I call it the billion sensors array. And we are about there to have enough fiber optic to do that. And the curve is exponential because of technology like 5Gs that are very bandwidth hungry, or in general, the development of the internet economy. So the challenge here is that for each kilometer of array, we have 0.5 terabyte of data a day. So really sophisticated data sciences, data processing in real time, data compression, as well physics-based inversion is crucial to take all the value for building sustainable and resilient cities. And I will stop here, and thank you again for the attention.
Okay, thank you very much, Biondo, and thank you to also to Catherine and Rahul for their presentation. So we have time for a few questions. I do want to start by mentioning something that some of the people in the audience might be aware of, and it's the fact that Stanford has a new initiative that is actually going to be launched very, very soon, has been announced by the president in the last few days, and is the creation of a completely new school in the university. So we were mentioning before that there are these organizations structured at Stanford, the School of Engineering, and then all the other schools. It turns out that because of the importance of the theme of sustainability, Stanford is actually approaching the problem by organizing a new school, a school of sustainability. The name is not very clear, but the theme is certainly going to be sustainability. So I wanted to perhaps ask Catherine and Biondo, who very likely will be very much involved in this new initiative. What do you think about it? What the perspective is? What the opportunities perhaps are with sort of this large new endeavor that Stanford is taking? Maybe Catherine, you want to say a few words?
Sure. Yeah, we've talked about this quite a bit in our department as this idea was kind of taking form. And I think the way that, a lot of people in our department are framing this is that for sustainability, you need three things. There is people, there is a planet, and there is profit. You could also say there is equity, the environment, and there is the economy. And for a system to be sustainable, you need to bring these three things together. The system has to be good for people, it has to be good for the planet, and it has to make profit. Otherwise, it's not going to be sustainable on the long run. So obviously, to get to systems like this, you need people who are experts in all of these three, right? You need environmental engineers, you need people who think more about the social context than people who think about health. You need people who think about the economy. Law also comes into play there. So getting to a sustainable system requires a lot of inputs. And I think it's very interesting, or it's going to be very interesting to see how we manage to get that together into a school. I think it's a big challenge, but I also think it's a very good challenge to try and address, because in the end, in the real world, we need to get to bringing all of these things together too. How that is going to take shape in terms of research is probably a little more clear than how it's going to take shape in terms of education and getting some sort of educational program. Making sure that you keep interdisciplinary depth in terms of the systems themselves, right? And having people really understand the physics behind it and the economical principles behind it, the health and everything. It's a big challenge, but I am very excited because I do think it could really have an impact if we manage to bring all of these things together. The starting point is, what does everyone understand under sustainability? And that is a discussion that I think will have to take place as well. Yeah.
Thank you, Catherine. Yeah, very, very good insight. Biondo, do you want to say a few words about it as well?
Oh, sure, I will be happy. First, I will echo the most of what Catherine said. And I do think that is an exciting opportunity for Stanford to have a real impact in the real world of the problems of today. I think that is exciting that we will put science, technology, and engineering as a focus of this effort. And that we'll have a chance, as Catherine mentioned, to work with social sciences, business, and law to make sure that we have sustainable solutions. The point that I would like just to add to Catherine is that part of the effort, there are two components of effort that is going to be beyond a school. One is an accelerator. So that might be relevant for the audience that I assume that mostly work with commercial companies or with governments, agency of some kind. So is really the idea is to have a faster translation of the knowledge and technology developed at Stanford into the non-academic world. And so there will be a clear effort by creating this accelerator. The model, the analogy is not exactly right, is not exactly the same, is the one of the Stanford Hospital as it relates with the School of Medicine. So the school will relate to this accelerator in an analogous way. Another way, now one that is going to be important for our undergrads and maybe some of our grad students, is a sustainable neighborhood in which there will be a set of buildings that are both residential and office and research building that will be really testing out in the real world some of the solutions that will be developed by the research by all these different schools. And I think that I will stop here, and thanks for the opportunity to put some well-deserved spotlight on this new effort.
Yeah, let me just add that I think it shows the commitment that Stanford has to this team. I think the idea of bringing these things together at least shows that there is an intention of sort of scoping out this field in a more organized way. There is a question I want to bring to Biondo again from James Cross. How robustly can the different seismic events, traffic, weather events, geological events be classified?
Is quite a bit. Of course, this is a new data acquisition, so we are learning as we go. But I think that we have clearly can now have another neural network that can identify and classify cars and trucks and buses going around campus. When Fantine tracked the Marguerite and checked how that was consistent with the schedule. Or we can find earthquakes. One of my previous students has a network on the East Coast and found storms and listened to concerts. But the real idea here is that we are going to have very densely sampled, spatially sampled data. So a lot of what we've been developing in seismic imaging, I've been doing for the past too many decades, can be brought to bear to work on this data that is going to be spatially dense, sampled, and very large frequency band. I didn't touch that, but you go from a fraction of a hertz to the kilohertz. And as such, you can capture all different kind of events, from the very slow moving ones to the very fast moving and high frequencies.
Very good. There is maybe time for a final question from Rodney Lessard. This is for Rahul. When will quantum supremacy be demonstrated for solving a real world problem?
So it's hard to predict the future, but probably 10 to 20 years. And there is a good amount of people who believe never also. So the answer is really, really long term. Of course, in the short term, has been quantum supremacy in some form has been demonstrated by Google on this random circuit sampling problem. So really long term. I don't have a more hopeful answer than that. Okay, well, I think you're young enough to perhaps take advantage of it eventually, or certainly to contribute to it. Okay, I think we will stop here. I want to once again thank our speaker, Professor Catherine Gorley, Professor Biondo Biondi, and Rahul Sarkar for this very high-level overview of at least some aspects of computing and problems that affect our planet. As I mentioned before, we have obviously a lot more that happens in ICME. I want to make sure you have a chance to look at the research handbook that we put together. And also, we have a break right now for 10 more minutes, and then we'll come back with the two final sessions that will discuss the seminar series AI for Good that we had in the winter session, and then a sort of an overview and a discussion of some of the contribution of Stanford and ICME to the NeurIPS conference. Okay, so thank you again to all, and we'll see you all back in 10 minutes. Thank you.